This call is now being recorded.
Okay, so in the previous class, we started on module 5, that is implementing the embedded system. So, in the module 4 and 3, we had learned about the embedded system software as well as the hardware. And in this module, we'll be learning about the implementation of this embedded system, that is the hardware as well as the software. So, in the previous class, I had told you this one thing, that is, what do you mean by hardware software co design? So, traditionally or in earlier days, whenever an embedded system is being designed, first either the hardware or the software used to be designed individually, and after that they used to be combined. But the problem with that is it can cause a lot of design mistakes at a later stage. So that is a huge that gives a huge negative effect. And that is why now we have started with a co-design kind of manner of designing an embedded system. So in co-design, this is the process that follows. This is what we learned. Last class I had talked to you about this. That is, the first step in that is called as functional exploration. That means you are finding out the desired product's requirement. And the second step is you need to map them. And in the third step, we need to partition the functions into a software and a hardware, and we need to do the hardware implementation and the software implementation individually, and then we integrate both the hardware and software together. So that is what is called as hardware software co-design. And then we learned about the three parts of this core design. One is called as core specification, second is called as core synthesis, and the third is called as core simulation. So what is core specification? Core specification means you develop the system specification which gives the hardware software module. So you give the specification of the hardware and the software. That is the first one. The second part is called as core synthesis. Core synthesis means we automatic and semi-automatic design of the hardware and software module. First, you specify what is required in the hardware and the software, and then you start the designing process. And that designing process is called as core synthesis. And after you design, after you specify, and after you design, you need to simulate, and also you need to verify whether your design is proper or you're getting the right results. So that is the third part. So the three parts while designing any hardware software co-design is: one is core specification, second is core synthesis, and third is core simulation and core verification. So we learned about what is system partitioning. So we need to partition the system into a hardware and a software. So the partitioning can be done either as partitioning the system specification into different tasks, or you can determine the performance of the function, or you can divide them into various elements. So these are different ways in which you can partition. And for any embedded system, these partitioning requires or represents a physical partitioning of the two system functionalities. These two system functionalities are the hardware part and the software part. So this is how much we had learned in the previous class. Okay, so in today's class, we'll be learning about different design patterns. So when you design the hardware and the software, you need to learn about various design patterns. So I think when you see in this slide, you might see some very familiar terms because these terms you have already learned in your, I think, your second or first module. You have learned about the state diagram, data flow diagram, control data flow diagram, and then we have a DAG, directed acyclic graph. So the first three diagrams or the first three graphs you have already learned in the first and second module. Because of that, I'm not going to teach that right now. If a question regarding that is asked, you have to write whatever you have learned in your first and second module about what is a state diagram, what is a data flow diagram, what is a control data flow diagram. You should be able to explain what is meant by that, what is an explanation of that, an example of that, and if an application is given and you are given a question to draw a state diagram, draw a data flow diagram, draw CDFG, that is control data flow graph, you should be able to do that. So all these things we had done, we had learned in your first and second modules. So that first three design patterns, I'm not going to repeat teaching that. Today we're going to learn about the fourth design pattern, which is called as directed acyclic graph, or it is also called as DAG. So what do you mean by DAG, or directed acyclic graph? So in a DAG, this is how, this is an example of a DAG, that is a graph. So the arrows, you can see two arrows here and two arrows here. So these arrows represent the dependence relation, the relation between the terms A and B, or B and C. That is the arrow representing. And the arc values, you are seeing some values here, right, in front, on top of the arrow, or right side of the arrow, you are able to see some numbers. So these values represent the communication time, how much time it takes to communicate between these two cycles, or between these two tasks. So the arrow represents the dependence relationship, and the arc value represents the communication time. And then precedence dependency captures the order of execution between the nodes. So nodes, I think you would have learned, you remember learning in the first two modules about nodes, what is meant by node. All these are called as nodes. So the order of execution between nodes are captured and can be executed in parallel. You can do it at the same time. And in this DAG, or directed acyclic graph, we have a specific partitioning structure. So this is the specific partitioning structure. These are the different stages in the partitioning structure of DAG. One is called as specifications. First, you need to specify. Then profiling. Then LD means longest delay path search. You need to search for the longest delay. This is the algorithm which they follow, the algorithm structure. And then they map, and then they schedule. So what do you mean by each of them? So first is profiling and building an initial DAG. So first, before you design the structure, you need to design the graph. That is this DAG graph. So while you design this DAG graph, you need to first find the longest delay path in DAG. So any application, you have various tasks. So you have to check which task, when you do which task does it cause the longest delay. Okay, longest delay time. So first we need to find the longest delay time. And then you need to map this longest delay path nodes to the hardware. The hardware part, this is where you combine the software path as well as the hardware part. So first you need to find the longest delay path, that is using a software, and then you need to map this longest delay path node to the hardware. The fourth part is schedule, and if invalid, mapping. Then if the mapping between the software part and the hardware part is invalid, then you go back to step 3, that is you start mapping again. So this is the advantage when you co-design. So when you start mapping, you understand whether it can be mapped, if there is any compatibility difficulty between the combination of the hardware and the software. And after that, you update the DAG and calculate the total execution time. After you do all these things, you need to calculate the total execution time. And if the system constraints are not met, if all these system constraints, even after you calculate the total execution time, it's not able to give the right result, it will go to step 2. Step 2 is again finding the next longest delay path. Otherwise, you quit. So this is the basic structure of the DAG structure. So I hope you remember in your data flow graph, how is the structure, in your state diagram, how you draw the structure, how you draw in the control data flow. And in directed acyclic graph, this is how the processes. It's a little more complicated than the other three. And in this DAG based partitioning system, the profiling collects the following data using different methods. The first is hardware or software execution time. So, hardware and software execution time is being collected. How much time the task takes to complete its task. That is hardware or software execution time. Second is hardware area. Third is amount of data transfer, how much data is being transferred. Then the execution order, which task has to be performed when. Then the data dependency between the nodes. So these are the different things that the profiler collects. Okay, the data that the profiler collects. Before you do all these things, you need to collect all these data. Only then you will be able to find out which is the longest delay path, etc. So what is meant by longest delay path search? It means longest execution time path. Which task or which path takes the longest execution time? So here you can see some tasks. So A, B, C and D, you can take it as different tasks. So you can see from A to D we have a path. From A to B we have a path. From A to C we have another path. So we have three, and then C to D also we have a path. So here we can see very clearly that the longest delay path is from A to D. Okay, so that is what is called as longest. The task which takes the longest time to execute it is the longest delay path. So that is one of the most important parts, that is finding the longest delay. And the second is mapping. So first you find longest delay path and then you map. So mapping means it maps a node or a task to be implemented as a dedicated hardware unit. That is, you map, and when you map, it can change the longest delay path as well as the DAG. And mapping of a node is valid if implementing the node to hardware gives the shortest delay path. So when you map the the software and the hardware, you will be able to know which is the longest delay path, and if there is any difficulty in the mapping between them, it has to go back to the previous stage of finding the longest delay path again. Then the third step is scheduling. So scheduling means it schedules the earliest node task first. Which task performs first, like how in the fourth module you had learned about the earliest deadline. So it's saying like that, earliest node task first. Which task performs first? So accordingly, it will be scheduled. That is scheduling. You need to schedule the different tasks. So these are the different steps that have to be followed while you draw the structure of a DAG. And before you compile or before you start the process, there is a very important procedure that you have to follow, that is to consider the optimization which can be applied to the source code of the embedded software. That is, if there is any optimization effects that can be expressed in the source program or the source code, it has to be done, because it is very necessary to consider cases in which it may be necessary to annotate the source code with compiler directives and hints. So there might be required for the programmer to give the hints that are required in the source code, so that if someone else reads the code, he is able to understand whether it is right or wrong, or to give him help. Okay, so that is high level optimization. So the next part is simple loop transformation. So this part I'll take in the next class. So today we learned only about this DAG, that is directed acyclic graph. So in directed acyclic graph, you have different stages, that is specification, profiling, longest delay path search, mapping and scheduling. Only after you complete each of the stages, you can go to the next stage. Okay, um, so this is a little more complicated, but at the same time, it is more accurate than the other graphical representations. Okay, algorithms. So now what I'm going to do is we have the same from this same topic, that is directed acyclic graph. I'm going to show you a video. So all of you are going to watch the video now, and after while you watch the video, in between you will have questions which you have to answer. Okay, so I'm going to post the link here. I'll post the link. I've already posted the class code as well, so you can either open through that or you can just click on this link where you can see the video. Watch the video fully. Please sign in with your college mail. Okay, please sign in with your college mail in this Edpuzzle. I'll just So this is the site. I just posted the link in your in the